Hello everyone, my name is Asa Sands, and welcome to another statistical anomaly video. Today we're going to be covering the politics of statistics. What is and why we PHack? So, p-hacking is something that happens in articles and research. And articles and research are really important because they provide us insight into our world, our reality, they give us knowledge, and they overall increase our livelihoods and our lives. Ideas are formulated with the express purpose of being exposed to their peers for dissection and sometimes even ridicule. This kind of environment allows for scientific advancement, as great and even groundbreaking ideas can be shared and investigated in an entire field in a really short amount of time. Most professionals in a field keep up on their field's research by reading those journal articles as well. So the benefit that these publications have in our lives is unquestionable. But nothing's perfect. Every system has drawbacks, and that's what we're going to be covering today. This video is going to speak directly to the problems of statistics, publications, p-hacking in this field of psychology. My bachelor's degree is in psychology, so the problems I'm going to be talking about are pretty familiar to me. So let's lay out the politics. There are three main things that are rather political in idea that really hinder publications and articles and p-hacking in the field of psychology. Universities are a big problem, actually, because the vast majority of psychology studies come from university campuses. That means that the demographics that they're running on these studies are the exact same kind of people. They're predominantly female. They are adults from their early to mid-20s. They're also predominantly white because minorities are very unlikely to get into higher education as opposed to whites, especially when it comes to grad school. So that means we're relying on female 20 to 30s that are disproportionately white for the vast majority of our psychology studies. That's a really big problem. Second, professors are often required to publish a certain amount of articles every year to keep their tenure and sometimes even their job. That's a really big problem, especially since actually making an article and publishing it is a really arduous process. Let's go over that. What do you need to do? You need to write a literature review. You need to do your method planning, how you're going to actually run the study. You need to submit it and get through an IRB. You need to recruit your participants. You need to run the study. You need to analyze your results. That's where the majority of p-hacking happens. And then discussion sections afterwards, which is often the longest part, besides a literature review. And then you have to actually find a journal to publicate through. That is just like, oh man, that takes a lot of time and a lot of energy. And that leads us into our third point. Journals will only publish you if you have a significant p-value as your result. If you don't have a significant p-value, well, better luck next time. What do? Often that study gets thrown into your file drawer, or pretty much the trash bin, where all studies unpublished go to die. And they never get seen. They never see the light of day. They are never heard from ever again. They are wasted time and wasted effort. And if this happens multiple times, people can lose their job over this. It's a really big problem. So, since p-hacking is so tied to the idea of p-values and significance, we're going to cover p-values and just make sure that everyone knows what p-values are and make sure that they're on the same page. So a p-value is a significance value. If you have a p-value that's less than 0.05, which p-values range from 0 to 1, if you have a p-value that is less than or equal to 0.05, then you're good. You're set. That is a significant p-value. If it's above 0.05, then that is not significant. That is bad. Nobody will publish you. If you have a p-value that's 0.0500001, close but no cigar. You can't get published anywhere. And that's because it's a hard cutoff, which is another big problem. What is really the big difference between 0.0500001 and 0.05? Really nothing at all. So I don't know why that's such a hard cutoff. P-values, in their essence, though, means what's the chance that you're wrong? If you have a p-value 0.5, then there's a 50% chance that you're wrong, which is why sometimes you'll say my p-value is 50%, something like that. If your p-value is 0.05, which is industry standard, then there's a 5% chance that you're wrong. And if you have a p-value of, for example, 0.024, then there's a 2.4% chance that you're wrong. So does that mean that we're wrong about 5% of the time? Well, yeah, as an industry, we are okay with being wrong about 5% of the time. Of course, this risk is mitigated by replication studies and lots of other studies kind of studying the very similar realms of thought and idea within psychology. So this is mitigated, but as a general rule, yeah, theoretically, we're okay with being wrong about 5% of the time. Next up is hypothesis testing. The study that we're going to be covering that's talking about a solution to p-hacking, or at least discovering p-hacking, kind of touches on this idea of type 1 and type 2 errors. So above here on our kind of upper x-axis, we have reality, what is really happening. And then our answers on this y-axis over here are, what do our statistics tell us? So if we conclude that there is an effect, we get a p-value less than 0.05, we are significant, and there really is an effect there, then we got the real result. There's no errors. Same thing. If we say that there's no effect there and there really isn't, then that's great. That's a real result. We're totally fine. This is where we start running into problems. If we say that there isn't an effect, but there actually is one, then we made a type 2 error, which is a false negative. We said that there isn't anything there when there actually is. And the opposite is when we say that there is an effect here, there is something that to be seen when there really isn't, that's a type 1 error. That's a false positive. To help you remember this, you can take false positive and false negative up there respectively for type 1 and type 2 errors, and you can pull down the first letters of each word, FP and FN. Then you're going to count the stems. As you can see here, F and P both have 1, F has 1, and N has 2. You just multiply those values, and you get 1 for type 1 error, and you over here, you get 2 for a type 2 error. You get type 1 and type 2 errors, false positive, false negative, respectively. It's a good little trick that I picked up to kind of remember the difference between the two. So let's move on to statistical power. Statistical power is a much simpler concept. It's a lot easier to explain. Statistical power essentially means that the more of it you have, the higher chance that you have of getting a significant p-value when you do run your statistics. So imagine that you just got the simple graph here. On your y-axis, you have your statistical power, and on the x-axis, you have your chance of getting a significant p-value. And it's pretty much a linear relationship. Of course, this is an overly simplistic graph, but here's a kind of a table that explains it a little better. Statistical power, when you have 15% statistical power, your chances of getting a value that is less than 0.05, a p-value less than 0.05, is 15%. That is a really woefully underpowered study. When we get to industry standard, which is 80%, so here at 79, really close, you have a 79% chance of getting a statistically significant p-value when your power is at 79%. So you might say, well, then why don't we just have all of our stats go at 100% statistical power so we always get a p-value? Well, there's a really big problem with that. Let's put our statistical power on this spectrum here. Let's put 0% on that side, 100% on that side. The closer you are to 0% statistical power, the more likely you are to make multiple type 2 errors, or many. The more you get, the more you're going to make. So then, on the other side of the spectrum, if you have 100% statistical power, or the closer you get to 100% statistical power, you're going to be making more and more type 1 errors. And that's why industry standard is right at 80%, because it mitigates the chance of having as few type 1 errors for as few type 2 errors. We just try and get right in the middle there. So we're making as little as both as possible. And that's why most tests are around 80%. And the study we're going to be covering is going to be emphasizing that. So the study we're going to be covering is called P-Curve, A Key to the File Drawer by Simmons, Nelson, and Simonsohn, which was published in 2014. Here is their abstract. Because scientists tend to report only studies, publication bias, or analyses, p-hacking, that work, we've already talked about that, readers must ask, are these effects true, or do they merely reflect selective reporting? We introduce P-curve as a way to answer this question. P-curve is the distribution of statistically significant p-values for a set of studies, p-values that are less than 0.05. Because only true effects are expected to generate right-skewed p-curves, containing more lows, 0.01s, than highs, 0.04s, significant p-values, only right-skewed p-curves are diagnostic of evidential value. By telling us whether we can rule out selective reporting as the sole explanation for a set of findings, P-curve offers a solution to the age-old inferential problems caused by file drawers of failed studies and analyses. So essentially they're saying P-curves are a really great way to detect whether people are p-hacking. And if you can't detect any p-hacking through running a P-curve, then the studies that you're reading are probably totally legit. So let's actually look at what they found, what the results were. Real fast, they talk about right skewed graphs, and we'll also talk about left skewed graphs. So I want to make sure we're on the same page as what those mean. This is a left skewed graph. And you can see here, if I put a person up there who's dabbing, you can see the person is on the left side of the graph. So it's a left skewed graph, even though the hump, like the camel hump over there, is on the right side. So it's really important to note that the skew is where there is little data. It's where the tail is on the graph. And then the opposite, that is a right skewed graph because the person who's dabbing is on the right. So just kind of remember that as we're looking at these graphs, remember which ones. Right skewed graphs are the good ones, left skewed graphs are the bad ones, at least in this specific scenario. So when we look at this here, you can see when power is completely irrelevant, it's not there, power is, statistical power is not present, every single p-value has an absolute equal chance of being selected. And the reason why this is from 0.01 to 0.05 is because, guess what? If you have a p-value of 0.05 or high, or if you have a higher value than 0.05, you ain't getting published. So you're never going to find p-values higher than 0.05, which is why they didn't even look at them in the study. That is already indicative of a really big problem. So there we go. It's a uniform distribution. They say here, though, that every single p-value has a chance of getting a 2.5. Those 5 have a chance of getting a 2.5 together. That means each and every p-value has a 0.5% chance of getting selected by random. That doesn't make sense. I think that's a typo, specifically when they say in this excerpt, it follows that 0.04 to 0.05 should occur 1% of the time, and 0.3 to 0.4 should occur 1% of the time, etc. When a studied effect is non-existent, every p-value is equally likely to be observed, and the p-curve will be uniform. So I don't know if that's a concept that I don't fully understand as to why that's 2.5, or if that's just a typo. If you know the answer to this, if you could write that in the comment section below, I would really love to know why that says 2.5, if there is a reason for that. So let's move on to power is 15%. As you can see here, it's no longer uniform. You can see that the left side of the graph is curving up, meaning that the more statistical power that you have, the more likely you are to get p-values of 0.01, as opposed to pretty much any other value. That means it is turning into a right skewed graph. Remember the person dabbing. Let's make it more obvious. 46%. That's there, same trends, 79% chance. This is a properly powered study. 70% of all properly powered studies should be around 0.01 p-values, whereas only 4% should be at 0.05. So that is a truly right skewed graph. That's what a proper non-PHacked set of studies should look like. So let's look at what they actually found. We expect these experiments to not have been PHacked. Again, we expect these were not PHacked. You can see here, clearly a right skewed graph. You've got a majority of p-values at 0.01 and a very few at 0.04 and 0.05. Of course, I look at this and go, there's probably a little bit of p-hacking going on here. I mean, you can't draw any conclusions from this. You'd have to look at that data very specifically in that situation at those 2 data points. But that's because the reason why I say that is because people are probably nudging their studies just over 0.05 so then they can get it publishable. And that's why there's this 3 times increase from 0.04 to 0.05. But I can't prove that. I can't conclude that. That's just a little inkly feeling that I have. These experiments, however, this is a journal where they collected other studies, a completely different journal, and they found that these experiments probably were p-hacked. You can see here, not even close to a right skewed graph. This is the exact opposite. This is a left skewed graph. The vast majority of studies are happening at 0.04 and 0.05, and underwhelming numbers at 0.01 and 0.02. There's absolutely nothing there. And you can see there on 0.1, studies contain evidential value. 0.999 is their p-value. That's absolutely nothing. That's as close to non-significant as you can get. So you can see here, don't read anything from this journal, whatever journal this is, because the vast majority of their studies have been p-hacked. You wouldn't get anything from this journal. So how do people actually p-hack their studies? Well, one way is harking. Harking is hypothesizing after your results are already known. It's like hindsight is 20/20. Of course, you're going to make the right conclusion after you look at what the answers are. Data snooping is specifically targeting data points or data that you want to study when it already confirms your hypothesis. So let's say you want to do a study on how black people are getting much less money than white people. then you go out there and you pick the 10 richest people in the world who are all white, and then you find 10 homeless black people who have no income, and then you say, look, there's a difference. Well, yeah, duh, you totally data snooped. If you want to do it correctly, you randomly sample from white people and black people, and that's how you actually draw that conclusion. So that would be data snooping. Construction of measures or building measures that are skewed towards your hypothesis, so they're just going to naturally lend themselves to confirming your hypothesis. Merging or manipulating your scores. That's like, hey, I've got this person here whose happiness index is at 8. I want him to not be an 8. I'm going to change him to a 5. Oh, yeah, okay, that's manipulating scores. Big no-no. Cherry picking. Let's say you ran 5 statistical analyses. 3 of them were not significant. You only report the 2 that were. That's cherry picking. So what are we actually doing to solve this problem? As it stands right now, most academics submit their articles for publication after they've already done everything. That means that they've gone through literature reviews, methods, IRBs, recruited their participants, ran the study, and then analyzed the results. Right here is where they're going to throw it in the file drawer, or really the trash can, or whether they're going to PHack, or whether they actually really did get a significant p-value. So if they're going to PHack, this is probably where they're going to do it. I would say they can do it earlier, but they can most of the time they're going to do it here. But also, this is where if they're moral and they won't PHack, or they just haven't, because not all p-hacking is completely conscious decisions, then, well, they're just going to toss in the trash can here. But if they do get a p-value that is significant and they actually can get published, then they move on to discussions, and then they have to find a journal that will actually publish them, which even then it can still be difficult. So that's already a really arduous process. Open Science Framework, which is an example of an organization that's trying to make the system easier, is a great example of changing the mold, changing the pattern. What they do is they allow publishers, or authors, the researchers, to publish their data online. Full transparency, anyone can see anything that they publish up there. They put it up there, anyone can go in there and say, hey, this is the exact kind of statistical analysis that they ran. This is how they did it. This is the kind of conclusions that they show, and everyone can get access to your exact data. And that opens transparency and lowers the chances that people could get away with p-hacking if they do p-hack. Or even be called out if they accidentally p-hack, which it is possible to accidentally p-hack. Not all p-hacking is malicious. It also opens up communities to talk to publishers about changing how publishing works. This is one of the most popular ways that is kind of coming up in psychology. It's still not really big, but it's coming up. And that is changing where publishers will agree to publish articles. Right now, as it stands, you have to wait until the end. But now, some of them allow you to write a literature review, write your method plannings, get through an IRB, and then they say, give us everything that you've got, and then we'll make a decision on whether to publish you when you're done based on how you're going to run the study. If it is scientifically sound and they really think that you're going to find something interesting that they want to publish, they will agree to publish you even if you don't get a significant p-value. That means you don't need to do the rest of these parts in order to get a published journal. That is a huge benefit. Not only are we going to have an increased transparency between researchers and publishers if this becomes more of a trend, but you would say goodbye to a lot of the file drawers out there. You get a lot more published, really interesting and scientifically sound studies. You'd have fewer type 1 and 2 errors. You'd have more job security for these researchers, less incentives to p-hack. You'd have more reliable studies, more sound methods, more replication studies, which still really needs to happen, and everyone's data is going to be more available. It just loops back into the more transparency, and oh gosh, it's just a really good cycle, and that is good for everybody. These are the changes that need to happen. This is in no way an exhaustive look at p-hacking or its effects on the field of psychology or other fields, but hopefully this was a good starting point for you to understand what p-hacking is, its harm to academia, and just the raw unfairness it reflects in the system of article publication. Please leave your thoughts in the comments section below. Hit that like button if you agree that we could be doing something better to combat p-hacking and rework the publication system, and subscribe if you want to see more videos like this one. Thanks, and I'll see you in the next one.